Dear students, detailed civil engineering courses like manual building design, Stat Pro, ETAP, SAP, Revit, AutoCAD, Primavera, P6 are available at Civil Engineering Shravan online application app. So download the application from the Google Play Store now. Each course contains 50 plus high quality video contents and free PDFs and exercises, and online certification will be provided after completing the course. Course will be available at 67 to 70% discount now and valid up to 6 months. Download civil engineering application now from Google Play Store, or direct link is available at the description of this video. Try to utilize this offer. Hello students, welcome back to my YouTube channel Civil Engineering by Shravan. So in the previous videos we are done with complete pile foundation design by using Stat Pro V8i software according to IS456 2000 code provision standard system. So in this video I will cover you the complete concepts related to how to design the cantilever slab design according to IS456 2000 code provision standard system as per the manual method. So this is one of the most important topic in the structural analysis and designing. Those who are really wanted to design the slab member which is related to the cantilever slab by using manual method, this is the right video for you. So these are the simple steps. I was explained some basic 7 steps. In these basic 7 steps, the 6 steps are important except the 7th step. So why? Because shear check was satisfied for the cantilever slab section. That's why 6 steps are important. So firstly I will explain you the complete typical floor plan for this cantilever slab. So this is the typical floor plan and I will explain you details about this. And these are the steps which is considered for this, and these are the step-by-step calculation which is showing for the cantilever slab design by using IS456 2000 manual method. Okay, I will upload this PDF in Civil Engineering Shravan online application app. You can download that PDF in the free PDF section which is available in the Civil Engineering by Shravan online application. The app link is available in the below description of this video. You can download that app for free PDF. Okay, so here you can see this is the cantilever slab designing section PDF which is related to IS456 2000 code provision standard system. So now we can see this is the panels of the slab. Let us consider these are the panels which is consisting of S1, S2, S3, S4, S5, S6, S7, S8, S9, S10. So here you can see for the S1 section there is no support exists at this free end. Okay, so it is consisting of only one support section. So it is comes under your cantilever beam. So the panel which is connected between the two cantilever beams, generally we will consider it as cantilever slab. So for this whole plan section it is consisting of 1, 2, 3, 4 members of the cantilever slabs, and the rest of the slabs which is related to 1, 2, 3, 4, 5, 6 numbers which is comes under the simply supported slab section. In the upcoming videos I will explain you how to design the simply supported slab member by using IS456 2000 code provision standard system. So I am developing a course which is related to complete manual designing of building structural model by using manual calculation method in Civil Engineering Shravan application. You can download that application for simple understanding of the complete designing of the manual method building structural model according to the real-time projects. So I was already updated Stat Pro software and ETAP software in our application. So if you want to really want the complete guidance regarding the Stat Pro ETAPs, you can download the application and you can install the application. You can watch the videos. So now we can see this is the width of this particular slab section and this is the length of this particular slab section. So now we can see I am taking length of this slab section is 1 meter in the horizontal direction, and width is also just I am taking here as 1 meter section. If you have another values you can consider the different values based on your consideration. But here you can see it is having 3 meter, not 1 meter here. But in this example just I am dividing this cantilever slab into 3 parts which is consisting of the 3 panel. Each panel I am considering here as 1 meter for the simple calculation of the designing section. Okay, you can consider the same amount of the reinforcement section for this particular panel, for this particular panel, for this particular panel. So remember this, we have to consider the unit width of the slab. Okay, so unit 1 meter width of the slab for the designing. Okay, so we will start designing of this particular S1 section which is nothing but the cantilever slab section 1 by using manual method as per IS456 2000 code. The following are the steps we need to consider for the designing of the cantilever slab as per IS456 2000 code. In that first step is to calculate the depth of the slab. This is one of the most important. Basically in the slab designing section we not need to assume the value of the depth of the particular slab. we have to calculate that value according to the considerations of the specifications like grade of the steel, again percentage of the tungsten steel we can calculate. And next step is to related to calculation of the loads. So for this particular single story slab section, I am considering only the loads comes under the dead load as well as the live loading condition. So I will explain you in this particular step. And the next one is related to bending moment and moment of resistance. Initially we will calculate the bending moment. The values which is obtained from the loads, we will calculate the bending moment. So from the bending moment, we will assume the moment of resistance for the balanced section. So which is having the formula is RU max into BD square. Okay, basically we will consider for the balanced section. Okay, so next step is to calculate the main steel. Again, next step is to calculate the deflection check. And next step is to calculate the distribution reinforcement bars. And next step is to calculate the check for the shear. So for this particular slab section, I am assuming M20 grade concrete provision standard system as well as the grade of the steel is 415 grade steel. Okay, so let's start with the designing of the cantilever slab by using IS456 2000 code provision standard system. And if you are not yet subscribed to my channel, please click on subscribe button and click on bell icon for more interesting updates on civil engineering topics like manual designing methods and complete courses and related to stat pro, e-types and everything. Okay, so if you want to complete guidance regarding the civil engineering concepts and civil engineering topics, you can download my application, Civil Engineering Shravan application, which is available in the Google Play Store. The direct link is also available in the below description of this video. Okay, this PDF of this particular calculation sheet is available in the PDF session of Civil Engineering Shravan application. You can download that you can download this PDF and you can check the values related to complete calculation which is comes under the cantilever slab. So now our first step is to calculate the depth of the slab. Basically we have the depth of the slab formula calculation which is related to span of the slab which is divided by modification factor, and we have to consider RB value. Okay, RB is nothing but the length of the slab as well as the width of the slab we have to consider for this particular section. Okay, so the RB value will be depends upon the type of the slab section, whether you are considering the cantilever slab section or simply supported slab section or continuous slab section. This RB value is directly available in IS Codebook Provision Standard System from the class 23.2.1 class. From the 23.2.1 class, the value of the RB comes under 7 for the cantilever slab. So here we are taking only the cantilever slab, we have to consider the RB as 7 here. If you consider the simply supported slab, we have to consider 20 for the simply supported slab. If you consider the continuous slab, you can consider it as 26 value. Okay, so here we are taking the span of the particular section which is comes under this as 1 meter section. So here I am taking, and for the cantilever slab L by BD is which is approximately RB value is 7 here. Now our next task is to calculate the modification factor. Why? Because we know the value of the span as well as the RB value which is obtained from the geometry of this particular building as well as the IS code book provision from the class 23.2.1. Okay, now our next task is to calculate the modification factor. So basically for calculating the modification factor, we required the FS value as well as the PT value. Okay, from IS code book also page number 38, it is having the curve which is related to the percentage of the steel and the value of the FS. Okay, so if you consider the percentage of the steel and value of the FS, it will be consisting of different types of the curves. Based on those curves, you can calculate the modification factor. So initially we will assume the value of percentage of the steel. So basically we will assume 0.15 value. If you want, you can assume 0.2 or 0.3, depends upon your consideration for the particular slab section. So here in this example, I am considering only the cantilever slab section only. That's why I am assuming less amount of the percentage of the steel here, which is of 0.15 percentage. So as just I am taking M20 grade concrete provision HYSD bar of 415 grade steel. Okay, so now we will calculate the FS value. The FS value is calculated by using this expression which is Fs equals to 0.58 into Fy value. So yield strength of the steel here. So we have to consider 0.58 into 415 grade. So if I consider this value, then it is comes under 240 Newton per mm square. This 240 Newton per mm square is the value we have to consider for the Fs value according to our calculated definition. So this is the first step which is related to calculation of Fs value for determining the modification factor. And we have to go to the curve based on the value of the Fs value which is related to the 240 and percentage of the steel 0.15. We had to consider the MF value, which is related to modification factor. So now we can see it is consisting of the 5 curves here, which is consisting of Fs of 120, Fs of 415, Fs of 190, Fs of 240, Fs of 290 value. Okay, you can consider the percentage of the steel which is available on the x-axis, again modification factor which is available on the y-axis. Now we will assume the percentage of the steel is 0.15, which is approximately laid here like this. So this is 0.2, 0.15 is here. Now we have to draw a vertical line which is related to 0.15 up to the part of this value of 0.2 up to the part of Fs of 240 grade. So now here I am drawing here like this. For example, let us consider this is the value which is coincided with 0.15 value. So we have to extrude this value in y direction condition system. So that particular value comes under modification factor we have to consider in the first stage, which is comes under approximately 1.85 value is the modification factor. By using the span, by using the modification factor, by using the RB value, we can easily calculate the depth of the slab here now. Okay. So now we will show, I will show you how to calculate the depth of the slab. So now depth of the slab D equals to slab divided by modification factor into RB value. So here the span of the slab is 1 meter. So that's why we have to consider 1000 divided by modification factor we are calculated here as 1.85 here, and the RB value which is obtained as 7 here from the IS codebook provision standard system 7. So which is comes under the depth of the slab is approximately 77.22 mm. Okay, but in practical situation it is not possible to consider the 77.22 mm thickness. That's why we have to increase the size of the particular slab section. Okay, so that's why just I am assuming the slab section by increasing some 2.88 percentage mm value, which is comes under the 80 mm value here. Okay, now we can see this is the first step to calculate the depth of the slab by using IS456 2000 code provision standard system. Now by taking the cover, just I am assuming here for this particular slab section cover is 20 mm. So if I sum this value of the depth of the slab and cover, then it will becomes under the total depth. Total depth of the slab is assumed as 80 plus 20, which is approximately equal to 100 mm. So this is the first stage for calculating the depth of the slab by using IS456 2000 code. So we are done with first step, which is related to calculation of the depth of the slab by using IS456 2000 code. Now our next step is to calculate the loads. Basically for this building structural model, I am considering the loads which is related to dead loading condition system as well as the live loading condition system, 2 load cases. And the optimal value of the load will be comes under the load factor of 1.5 times of dead load plus live load condition system. So initially we will calculate the loads which is comes under that particular slab related to dead load as well as the live load. Then we will sum that particular value and we have to apply the 1.5 factor for calculating the ultimate loading condition system. So initially we will calculate the self weight of the slab. So firstly I am taking that width of the slab is approximately 1 meter for that particular panel. So here width is 3 meter, but in that 3 meter also I am dividing that particular 3 meter to 1 meter, 1 meter, 1 meter panel. So that's why it is comes under width as 1 meter. Okay. So here we have to consider the self weight of the slab, which is equals to unit weight of the slab into area of the slab. So unit weight of the RCC generally we will take 25 into area of the slab, which is equals to length of the slab, which is multiplied by thickness of the slab. Okay. Now here unit weight is 25 we have to consider, and this is not the area of the slab, actually it is thickness of the slab we have to consider and length of the slab. Basically thickness of the slab is 0.1 meter and we have to multiply this with length of the slab is 1 meter, which is comes under 2.5 kilonewton per meter. 25 multiplied by 1 meter is the length of the slab and the thickness of the slab is approximately 0.1 meter, which is comes under 2.5 kilonewton per meter intensity. Now we will assume the floor finishing load, which is nothing but your marbles and tiles which is laid on that particular slab section. I am taking here as 1.75 kilonewton per meter. This value is also considered as per the IS codal provision standard system. And just I am taking live loading condition which is half of the original live loading condition system. Basically for the single story structural model we will consider 1.5 kilonewton per meter for the simply supported slab. So here I am assuming this particular slab will not be consisting of access which is required for this particular slab. That's why I am taking 50% of the live load when you compare with the simply supported slab. So here I am taking 1.5 divided by 2, which is approximately equal to 0.75 kilonewton per meter is the intensity of the live load just I am considering for this particular slab section. Okay. So this is the process of calculating the three types of the loads. One is related to self weight and second one is related to floor finishing load and third one is related to live loading condition. For calculating the self weight, we have to multiply the self weight of the slab with the length of the slab and thickness of the slab. For calculating the floor finishing load, we have to assume the code book which is related to IS456 2000 and live load we have to consider 50% of the cantilever slab which is comes under single story building. Now the total load equals to 2.5 plus 1.75 plus 0.75 which is approximately equal to 5 kilonewton per meter. This 5 kilonewton per meter is the load which is acting on that particular slab section. But we have to consider the extra 50% of the load as per the safety. That is comes under your ultimate load. When you apply the ultimate loading condition system on that particular slab, then the obviously slab will be obtained as cracks in that particular section. Okay. So that's why just I am considering ultimate load is, it is the multiplication of 1.5 times of dead load plus live load. We are already given the values of total load of summation of dead load plus live load which is approximately equal to 5 kilonewton per meter. So which is multiplied by 1.5 meter which is gives the value of 7.5 meter kilonewton per meter. Okay. So now we have to design this particular slab section which is used to resist this 7.5 kilonewton per meter moment load value. Okay. Now we have to calculate the moment, bending moment value. Next step is to calculate the bending moment and moment of the resistance. So the design moment for the cantilever slab is we can calculate as per WL square by 2. This is the bending moment which is comes under cantilever beam. Okay, we will consider the same formula for the cantilever slab also. So WL square by 2, W is nothing but your load 7.5, L is nothing but the length of the slab and we have to divide this particular value with 2. Then it will be comes under the value as 3.75 kilonewton per meter. Now we have to compare this particular 3.75 kilonewton per meter bending moment value with the moment of resistance which is required for the particular slab section. Okay. So now according to the balanced section, moment of resistance parameters are considered from this particular table. Okay. So here we are taking the M20 grade concrete provision with FE415 grade steel provision standard system. Basically, the moment of resistance value is calculated by using this expression RU into max into BD square. Okay, so RU value is considered from this code book which is of M20 grade 415 which is comes under the value is 2.76 value. Okay, so if you substitute the value of 2.76 then it will be comes under 2.76 into 1000 into depth of the slab we are assumed as per the calculation is 80. So 80 square into 10 to the power of minus 6. If you wanted to calculate this particular value to cubic meter value from mm to meter, we have to multiply this factor. So which is comes under 17.6 kilonewton per meter square. So according to the calculation part, it is approximately 4 to 5 times greater resistance value for that particular slab section. So hence the moment of resistance value is greater than moment of the value which is obtained on that particular slab section because of the presence of the load cases. Hence it is safe. We have to check that moment of resistance is having higher amount of the value or not. Okay. So this is our task. Now our fourth task is to calculate the main steel. Basically main steel is calculated from the code book formula which is having AST equals to 0.5 into FCK divided by Fy into 1 minus under root of 1 minus 4.6 into Mu divided by FCK into BD square into B into D. So this is the basic formula we have to consider for calculating the AST value for the main steel. Okay, so we have to substitute the value AST equals to 0.5. FCK is the grade of the concrete 20. We are already assumed that value. Grade of the steel is 415. 1 minus under root of 1 minus 4.6 into 3.75 which we are calculated here moment value 3.75 divided by FCK is 20 here. B value is width of the particular slab section. I am assuming here as 1000. And depth of the slab is 80. Okay, so we have to consider 1000 into 80 again, so that it can comes under the value of AST value is approximately 135 mm square here. Okay, so this is the process of calculating the AST value. Now we will calculate the AST minimum which is approximately equal to 0.12% of gross cross-section area of the bar. So for HOSD bar we will consider 0.125%. For mild steel bars, we can consider 0.15%. Now we will calculate that particular value, AST minimum value. So we have to multiply this 12% with length and width. Length is 1000, width is also 1000. I am assuming here, which is comes under 120 mm square. Now you can see this is the calculated value of the AST and this is the minimum value of the AST. So you can see here the minimum requirement of the steel is also satisfying as per the main steel calculation part. So here AST minimum is less than AST, hence we are calculated the safe, which is approximately equal to 135 mm square for that particular steel section. Okay. Now after calculating this, we will assume the 8 mm diameter bar. Just here I am in this example, just I am taking 8 mm diameter bar. If you want, you can take 10 mm diameter bar or 6 mm diameter bar depending upon your requirement. Most of the people will consider only 8 mm as well as the 10 mm diameter bar for the slab. That's why I am selecting here as 8 mm diameter bar. Initially, we will calculate the AST value for that particular diameter of the bar. So, which is equals to pi by 4 into d square, which is of 8 square, so that it can come the value as AST as 50 mm square. So, this is the value of the AST which is required after assuming the diameter of the bar. Now, we will calculate the spacing. So, generally we have the spacing formula which is equals to AST, small ast divided by capital AST. So, which is multiplied by 1000. So, which is equals to 50, which we are calculated here. And this is the 135 main steel. So, here AST 135 multiplied by 1000. So, that it comes the value of the spacing is 370 mm value here. Okay, but as per the IS code, we have to consider the maximum spacing as per through two specifications. So, one is related to 3D section or else 300 mm. This is the maximum spacing we have to consider for the slab section. So, if I consider the 3D, which is equals to 3 multiplied by 80 mm is the depth of the particular slab. If I consider, then it will be comes under 240 mm is the spacing between the bar which is required for the maximum, which is of 240, or else we can consider the 300 mm. But here you can see we are calculated the spacing according to AST as well as the AST value, small AST, capital AST, which is obtained as 370 value. So, we have to take these three values consideration. So, depends upon the minimum value of these three values we have to consider. So, here in this case the minimum value for this AST is approximately 240 mm. So, that's why we have to consider the 240 mm value for the AST spacing. So, now we have to provide the 8 mm diameter bar which is placed at 240 center to center distance for the main steel reinforcement bar. Okay, now we will calculate the AST provided for that particular steel, 1000 into AST divided by spacing. Why? Because we are fixed here spacing as 240. Now we will calculate AST provided 1000 into 50 by 240, which is approximately equal to 208 mm square here. Now you can see this is the 208 mm square value which is provided for this particular slab section as per the main steel reinforcement. So this is the reinforcement calculation which is comes under the main reinforcement calculation, which is having 8 mm diameter bar which is placed in vertical direction for the length of the particular slab section, which is placed at a distance of 240 mm center to center distance between the bars for that particular members. In the same process, we will check for the deflection for this particular slab section. So, percentage of the steel requirement we have to calculate. So, 100 multiplied by AST divided by 1000 into D. 100 into 135 we are calculated the main steel reinforcement divided by 1000 into 80, which is comes under approximately 0.17%. So here we have to compare this particular value with the maximum percentage of the steel, which is of 0.15% as per the IS code provision standard system for the HYSD bar sections, okay, or mild steel bar section, which is 0.15%. Okay, so for the HYSD bar, it is comes under 0.12%. It is greater than the assumed value is greater than 0.15% as well as the 12%. Hence, the design check is safe as per the deflection point of view. No need to check the detail check. If you have, you can check the detail check also. It will get the depth of the slab is approximately less than the 80 mm dimensions. Okay, so this is the calculation part which is comes under the main steel calculation. Now we will calculate for the distribution steel. According to IS codebook provision standard system, the distribution steel is considered according to 0.15% of gross cross-sectional area. So 0.15 divided by 100, we have to multiply this as length as well as the width of the slab. Then it will be comes under 150 mm. By assuming the 6 mm diameter bar, we will calculate the small AST value, which is approximately equal to pi by 4 into 6 square, which is of 28.27 mm square. Now we will assume the value of the small AST is 28 mm square. Now we will calculate the spacing. So 1000 into small AST into divided by capital AST. So 1000 into 28 divided by 150, okay, which is approximately equal to 180 mm. But as per IS code, we have the considerations for the maximum spacing also, for the distribution steel also, which is 5D or 450 mm. 5 into 80, which is approximately equal to 400 mm, 450. Here we are calculated the three values which is related to the spacing between the bars. Now we can see this is the spacing between the bars. So here 180 and 400 is there and 450 is there. We have to assume the minimum of this particular value. So minimum is 180 mm. So we are consider the 180 is less than 400. Hence consider the value of 180 is the center to center distance between the bar for the distribution steel. So provide 6 mm diameter bar with 180 mm center to center distance for this distribution steel. Now we can see this is the main bars and these are the distribution bars. So distribution bars are considered as 6 mm diameter bar, which is placed at a distance of 180 mm. Okay. So if you increase the diameter of the bar, the spacing value will be increases. So basically for the main bars, it is comes under the values approximately 240 mm center to center distance for the bars and 180 mm center to center distance between the bars for the 6 mm diameter bar. Okay. So check for the shear. Then generally for the cantilever slab section, shear check is not carried out. Why? Because it is automatically satisfy the requirement. Okay. So that's why I am not calculating the shear check also for this particular member. So in the next session, I will explain you complete to simply supported slab designing section by using a manual method as per IS456 2000 code provision standard system. Now you can see according to the considerations of the final reinforcement value, it is comes under 8 mm diameter bar, which is placed at 240 center to center distance, and the distribution bars, which is placed at 6 mm diameter bars, which is placed at 180 center to center distance, not 180. I will check that reinforcement value. So which is comes under the 180 center to center distance between the columns, bars for the distribution bars. So this is the complete calculation of the reinforcement which is obtained for cantilever slab section. If you have any queries about this video, please try to text me your questions in the below comment box. The free PDF is available in Civil Engineering Shravan application app. You can download that application, which is the download link is available in the below description of this video. So in my upcoming courses, I will explain you how to design a manual building designing section with each and individual points. Okay. So thank you for watching this video. See you in the next video.